Hey y'all, and welcome to the next section of practical packet analysis. And we're still in our discussion of protocols. We're moving up the OSI model, and we're to the transport layer now, where we'll focus all on the transport layer protocols. Now we're going to continue with our same approach that we've been using for the other protocol sections if you've been watching those. We're going to start by talking about the features and structure of each protocol. We'll look at the actual header structure and talk about different features as it relates to that. And then we'll also talk about stimulus and response, both normal and abnormal, what you should expect to see from transactions related to these protocols, and what would be considered abnormal and things you might want to watch out for either from a troubleshooting or security perspective. Now, the transport layer is interesting because we've talked about the network layer, and I said multiple times that the network layer is not reliable on its own. The headers were very simple. They didn't really provide any means for validating that packets actually got where they were going. There was no guarantee of two-way communication, no automatic responses, no error detection or recovery, none of those things. And that's because the place that happens is either going to be the transport layer or the application layer. But in this case, we're going to focus on how the transport layer provides those services. And the services it's generally going to provide are just that. It's going to provide reliability, flow control, and the ability to do congestion avoidance, detection, and recovery. So these are all things generally that we want when we need to make sure packets are actually reaching their destination. That's not to say these services have to be performed at the transport layer. They can be performed in the application layer, and we'll talk about when that makes sense and what transport layer protocol you would use when you want to handle that actually at the application layer. Now, for this section, there are only two protocols we're really concerned about. Those are the User Datagram Protocol, or UDP, and TCP, the Transmission Control Protocol. Those are the two primary transport protocols you'll see in nearly every scenario you examine, so that's what we're going to focus on. And these protocols are very, very different. They're not really complementary at all. They're very different and have very different, they perform some of the same tasks, but TCP is very concerned with reliability, where UDP is really more of a pass-through. It's a transport protocol for the sake of a transport protocol and doesn't really provide any reliability as you might expect. You generally use UDP when you have reliability measures at a higher layer, so at the application layer. So we'll show what I'm talking about there and go through all of that moving forward. Before we go any further, I want to talk about ports. And I'm talking about this now because it's applicable to all transport layer protocols. It's applicable to both TCP and UDP. And I want to explain it kind of conceptually before we get there and look at it, because ports are something we've seen thus far in some of the examples I've shown and I've kind of hinted at, but I've not actually explained ports. So I want to explain ports conceptually in the simplest way possible before we move forward, because that is a critical component of transport layer protocols, TCP and UDP. So in this example, say we have System A communicating with System B. And in its simplest form, System A sends packets to System B. System B receives those, hands the data from those packets off to the service that's actually using them, and everything is great. Everything works just fine. And in this example, System B maybe only has one service running. Maybe it's a web server. So it's got Apache or IIS or Nginx or some other web server running, and it's only receiving packet streams to that particular service, and everything is great. However, let's look at another example. Say we have System A and System B again, but in this case, we have multiple packet streams going from System A to System B. Or in this case, maybe we have multiple systems. Maybe we have System A, D, and F, and they're all sending packets to System B. And maybe System B actually is running multiple services. System B is running a web server, a DNS server, maybe it's a domain controller, maybe it's running an FTP server. It's got all those different services going. So how does System A, if it wants to communicate with System B on all those different services, how does it differentiate the packet streams it's sending? Furthermore, how does System B, when it receives packets, know which service to hand them off to? How does that work? Well, as you may have guessed, the answer here is actually ports. To illustrate how ports work, look at this diagram and how it's changed. Now, not only are we just sending streams of packets to System B, but System B is actually receiving those through specific ports, so to speak. So think of this just like System B is a wall, and there are holes in that wall that lead to particular services, to particular places. You can kind of think of it maybe like a post office in that sense. So with System B, anytime you establish a service or create a service that needs to receive network communication, it's going to be bound to a specific port, and that's what we're demonstrating here. So you see we have 4 services. They could be anything. They could be mail, web, DNS, FTP, any of those things. But each service is bound to at least one port, and that's to say that system will receive communication for that service on that port. So for a web server, it might be port 80. We communicate on these ports. They're numbered ports. There's a finite number of them. There's only so many ports available, and they are all identified by actual numbers, and that will actually be in the packets we're going to look at. So again, notice that in this case, System B has 4 services, and each one of them has a port assigned to it, and that's how System A knows how to communicate with it. However, there's a little bit more to this story as well. Look at this. System A actually has ports too, but it has transmitting ports. Can you think of a reason why System A would need ports if it's transmitting data and not receiving data? Well, the answer is in two-way communication. While System A is actually sending packets to System B, chances are System A is actually going to receive responses back from System B, right? If it's a web server, I'm sending a GET request, but I want to receive data back for that GET request. So in that case, System B has to know how to communicate back with System A, and it needs to know how to get that information to the right service that actually requested or initiated the communication, in this case, maybe a web browser. So because of that, System A, when it communicates with System B to a destination port, also has to pick a source port that System B then can communicate back to. So again, think of this whole concept at System A and System B. You can't just blast communication to them. It's a wall, and those walls have holes in it, and those holes link directly to services. So you have to route traffic, route communication in the right way to get to those different devices. So that's, I think, the easiest way to conceptualize ports. Again, you can think of it maybe like a post office, where based upon certain information in the address, they're being routed to the right place. This is all about getting communication where it needs to go and connecting network communication with physical services that are bound to specific applications that are running on the system. Now, a logical question here might be, well, what about a case of a web server where, sure, it has a port bound to it, maybe it's a port 80 system, but maybe you have hundreds or thousands of systems communicating to that web server. How does it differentiate those packet streams? How does it know one packet stream from another if it's all coming into the same port? And that's a little beyond our scope here. That's more of it's less of a network thing, more of a system thing, and it has to do with threaded applications. So applications can receive communication streams and place them into individual threads, or do session management, things about that. But those are services that are handled at higher levels of the OSI model at the application layer level in a lot of cases. So that's not really a network thing that we're concerned about at the transport layer. Nonetheless, important to understand how ports function conceptually, and hopefully this will make a little bit more sense when we go through the specific protocols, TCP and UDP, just a little bit later. So to sum up our discussion of ports, services bind themselves to ports to send and receive data. When transport layer protocols are used, a transmitting system must know which destination port it wants to communicate on for the recipient system. That's information that has to be included in that packet. And it also must choose a source port to receive responses back. And you might ask yourself, how does an operating system choose a source port? We know how it chooses a destination port because it knows that a service should be listening on a specific port, and that's probably something that's a configured setting. Well, source port selection can vary based upon operating system. Some will choose them at random. Some will choose them sequentially. So they may choose 3000 to communicate the first time and 3001 the second and 3002 after that. It's going to vary a little bit, but for the most part, it doesn't matter what source port you use as long as it's communicated in the packet and the destination knows how to respond back. Now, there are a couple of things we need to know about port ranges that are important. First and foremost is that the port range, all ports fall between 0 and 65,535. So that's a pretty big range there, and we subdivide it in a couple ways. First are your server ports, or your well-known ports that exist between 0 and 1024. They're called this because generally a lot of your more popular services that have well-defined, established, known port ranges fall within the scope between 0 and 1024. So that's why you see things like web and DNS and FTP and SSH and SSL, all those things fall within this range because this is kind of that well-known server-defined port range. It's also worth noting on some systems, to communicate on these ports, you actually have to have admin privileges. So you can't communicate on these, open up listeners, or communicate outbound on these ports unless you have those particular permissions. So that's of note as well. So that leaves our other group, which is 1025 through 65,535, and that is your ephemeral port range. And basically, you can think of this just as everything else. We call these, some people call these high ports, but generally when you see communication sourced from one device, it will generally be starting in this range. You really won't see a lot of source ports that are below 1024, but you will see them in this range. So these are not hard and fast guidelines. They're not something that's written in stone. Systems can violate these, and it's pretty easy for that to happen. And there are certainly a lot of well-known services that have that use ephemeral port ranges. So this is just a general guideline. It's not the gospel, but this is how we organize ports. The total range, the all ports range, that is the gospel. You're not going to see any ports above 65,535. But nonetheless, this is kind of our overview of ports, and it's important to keep in mind because we'll talk quite a bit more about ports as we move on into the next couple sections on UDP and TCP.